Today we're looking at how to convert fractions to decimals in the sexiest way possible with long division. Let's get started. So let's start out with a simple example. How about the number 1/2? Okay, how do we represent this as a decimal? Well, we already know what it is. It's going to be 0.5. No surprise. But how do we demonstrate that? How do we demonstrate this to be true? Well, let's use long division. Okay, what we're actually saying is 1 divided by 2, right? That's what this fraction represents. So how do we do 1 divided by 2 in long division? Well, we're asking how many times does 2 go into 1? Well, 1 is less than 2, so it goes in 0 times. And so instead we have to bring in a 0. Okay, we have to bring in a 0. Now we're going to ignore the decimal points. We'll keep it there to keep things lined up correctly, but I'm not going to talk about them as if they're there. We're going to think then, how many times does 2 go into the number 10? Okay, 2 goes into the number 10 5 times. Why? Because now we do 2 times 5 is 10. And then you're going to subtract this away, and what we're going to get is 0, right? 10 minus 10 is 0. This 0 is also known as a remainder. All right, so the answer here is going to be 0.5, and then after you have that, there's nothing left over. There's no remainder. And it turns out that when you get a remainder of 0, that means you're done. Okay, you could continue to ask how many times does 2 go into 0? Well, it goes in 0 times, and 0 times 2 is 0, and that's going to be a 0. And how many times does 2 go into the 0? 0, 0, 0, 0. Lots of zeros. We don't care about that, so they don't contain any more information. We're going to stop here. We have a terminating decimal of 0.5. Okay, so this is exactly what we were expecting, and we can demonstrate we get that using long division. Let's try another example. How about 3/8? Okay, what does that equal? So let's do this. We're going to do 3 divided by 8. Let's do the long division. Well, here again, we're going to get 0. 3 is less than 8. So now we have to bring in one of these infinite zeros here that we have after any number. How many times does 8 go into 30? Okay, well, 8 times 4 is 32, so that's too big. So we're going to be doing 8 times 3. 8 times 3 is 24. We're going to subtract that away. We're going to get a remainder of 6. Okay, a remainder of 6 here. Now, we need to bring in another 0. So that's what we're going to do. Remember, there's an infinite number of zeros we can bring in. Bring that down. We ask how many times does 8 go into 60? Well, 8 times 8 is 64. That's too big. So it must be 8 times 7, right? 8 times 7 is going to be 56. We subtract this off. We get a remainder of 4. And now we have to bring down another 0, don't we, right? Bring down another 0 here. 8 goes into 40, well, exactly 5 times, doesn't it, right? Because 8 times 5 is 40, and when we subtract that away, we get now our remainder of 0. Now, what I want to indicate is here we get these different remainders. All right, here's another remainder. Once we get to a remainder of 0, we know we're done. Okay, so 3/8 is the same as 0.375, and there we go. Okay, that's how we can do this kind of problem, another lovely terminating decimal. Let's try a decimal that doesn't terminate. How about 1/3? Okay, 1/3 we know should be equal to 0.3 repeating. Okay, a non-terminating decimal has an infinitely long with some repeating chunk in there. How do we demonstrate this using long division? Well, we're going to have 1 divided by 3. Once again, 3 goes into 1 0 times. We have to bring in another 0. And now 3 goes into 10 3 times, right? And 3 times 3 is going to be 9. So if we subtract that away, we get a remainder of 1. And now how many times does 3 go into 1? Well, we have to bring in a 0. So how many times does 3 go into 10? Well, it goes into 10 3 times. And 3 times 3 is 9. And we subtract that away, and we're going to get 1, right? This is repeating. Notice our remainder starts repeating, and thus the answer that we get must also start repeating, because we're just asking the same question over and over again, right? We're just asking How many times does 3 go into 10? How many times does 3 go into 10? How many times does 3 go into 10? So we're going to keep getting the same answer over and over again. And so this explains why things start repeating. Basically, the quotient starts repeating when the remainder repeats. And here the remainder repeats pretty early on, right? After just one operation, you get a 1 back out. And so that's why we only have one single digit in our repeating unit, because the remainder repeats after just one cycle through the long division here. Let's try another example. How about we try 2/11? What does that equal? All right, let's do the long division. So we've got 2 divided by 11. Okay, so 11 doesn't go into 2, so we have to bring in a 0. 11 goes into 20. Well, 2 times would be 22. That's too much, so only 1 time, right? 1 times 11 is going to be 11. We'll subtract that away, and we're going to get a 9. Okay, so now we have to bring down another 0. How many times does 11 go into 90? Well, it goes into 90 8 times, and that's going to give us an 88. We'll subtract that away, and what do we get? We get a 2. And now notice we have begun to repeat ourselves. Okay, so if we look at our remainder here, was a 9, remainder here, we started with a 2, so we're starting to ask the same question again, right? If we wanted to bring down another 0, we would just be asking, how many times does 11 go into 20? We already asked that question. It goes in 1 time. And then we're going to get an 11, subtract that away, we'll get a 9, and then that'll give us a 90. And that's going to go in 8 times, right? And so everything repeats itself over and over again. In this case, it takes 2 operations of long division before we get the remainder to repeat. And so that's why the result we get here is actually 0.18 repeating. We get 2 digits that are repeating because it takes us 2 operations through the long division before the remainder starts to repeat. Okay, so that's what we get here. That's our answer right there. Let's try a more difficult problem. Okay, how about 3/7? I want to know what 3/7 is going to be. All right, so that's 3 divided by 7. Let's do the long division. So we'll get nothing here. We'll have to bring in a 0. So 3 goes into 30. Well, that's going to be 4 times, right? So 7 times 4 is going to be 28. We're going to subtract that off. 30 minus 28 is just going to be 2, isn't it, right? Okay, well, let's bring in the next 0. 7 times 3 is 21, so that's too much. It must be only 2, right? So that's a 14. We subtract that off, and we're going to get a 6 as our remainder here. Still not done. Let's add in another 0. All right, 7 goes into 60. How many times is that? Well, 7 times 9 is 63, so that's too much. It must be 8, right? 7 times 8 is going to be 56. We'll do our subtraction here, and we're going to get a 4. Okay, let's keep going. We're not done yet. We got a 40. 7 goes into 40 5 times, right? So 5 times 7 is 35. We'll subtract that off. We get a remainder of 5. Well, I guess we're still not done, so we have to bring in another 0 here. 7 goes into 57 times, right? 7 times 7 is 49, so that's going to give us a remainder of 1, okay? We're not quite finished, but we're out of room, so I'm going to write the 1 up here, and we're going to bring in the 0 over here. 7 goes into 10. Well, that's just 1 time, right? So that's going to be 7. We'll subtract off. 10 minus 7 is going to be 3. And this is actually where we start to repeat, because this is the very first question we asked. We asked, how many times does 7 go into 3? And if you want to, you could bring in a 0, right? You could bring in this extra 0. How many times does 7 go into 30? Well, 4 times. Then you're going to get a remainder of 2. And then it's going to go 2, 8, 5, 7, 1. So here, we're finally done. We figured out that 3 divided by 7 is going to be 0.42857 repeating. There we are. Okay, so that is the result here of this entire operation. And it's a long number, isn't it, right? Notice that this has 1, 2, 3, 4, 5, 6 different digits here. And it kind of begs the question, like, how long can this repeating unit get, right? How many possible digits could we have in this repeating decimal? If I was to do, 4 sevens, could I get a longer number? Well, I guess this should actually be here. Okay, could I get a repeating unit that's, 20 digits long? Could I have a repeating unit that's 100 digits long? Is there some limit? Turns out, yes, there is. The key to understanding this is in looking at the remainders that we get here, because they're the key to the pattern. We know, for example, that it is impossible for us to get a remainder of 0. Why? Because once we get a remainder of 0, our answer terminates. We will not have an infinitely repeating decimal. So given that we're having some infinitely repeating decimal, we know we'll never get a remainder of 0 in any of these operations. We also know our remainder cannot be 7, because that's what we have here in the denominator, right? So every time we get a remainder, it's going to be a number that's less than 7. It's the amount left over after we do some number times 7 and then subtract it over here. We're going to get some number less than 7. So what are the possible remainders? Well, that means the possible remainders are going to be any number from 1 to 6, right? 1, 2, 3, 4, 5, 6. These are all possible remainders. And in this specific example, we actually get all of them, right? We have a remainder of 1, of 2, of 3, 4, 5, and 6. So we get all of those. But once you've exhausted all of the possible remainders, then you kind of have to do the next operation. You're guaranteed to get that some remainder back again, right? And so once we get through here, and we get through the operation with the remainder of 1, well, we wind up getting a 3 again, which is what we started with. There's no way to avoid that because there's only 6 possible remainders you could get. So once you've gone through 6 operations, you're guaranteed to start repeating, all right? So in general, if you call this number here, let's call this the denominator, well, then you're going to get the maximum possible number of repeating digits is going to be the denominator minus 1, right? So you can imagine if we had 3 divided by, 77, then it is possible you could get a decimal representation with 76 digits long. That's the largest possible repeating unit you could get. You could never go beyond that, though. You could have less. You could have, 1 or 2 digit repeating unit, or maybe it terminates. But you could never go over 76 digits if this was 3 divided by 77. So this sort of puts a cap on how long you have to keep doing your long division until you get your complete unit, till you've uncovered the entire decimal representation. Okay, I kind of want to do one more fraction conversion here. We're going to go with 375 divided by 24. So I want to do this one because this denominator of 24 is a big number, right? Previously, we always did smaller numbers. Bigger numbers sort of come with a bigger problem. Let's write this down. So we've got 375 divided by 24. The problem is that I don't know off the top of my head 24 times 6 or 24 times 9 or 24 times 3. I just don't know these numbers off the top of my head. I know the times tables, 7 times 7, 7 times 6. I know all of that, but 24, I don't know. So because I have this larger 2-digit number, what I want to suggest is that you create a little bit of a tool to help you. You create a little multiplication, little times table right over here, right? So what I'm looking at is 1 times 24, well, that's 24. And then 2 times 24, well, that's going to be 48, right? And then 3, I can add another 24 here. What am I going to get? I'm going to get a 72, right? And then you can fill this out. 4, 5, 6, 7, 8, all the way up to 9. These are all the possible combinations. And I've done this before, so let me just fill out here. We get 4 is going to be 96, 5 is going to be 120, 6 is 144, 7 is 168, 8 is 192, and 24 times 9 is 216. Okay, so I've created a little bit of a times table here, and that's just going to help us do the long division. Because if you're doing long division, it means you don't have a calculator, right? So it's better to sort of prep this up beforehand. All right, now let's do the long division. So 24 doesn't go into 3, but it will go into 37. It will go into 37 one time. So that's going to be a 24. And then we do our subtraction. And that's going to give us, what, a 13, right? Okay, so now we're going to bring down our 5. And how many times does 24 go into 135? Well, we're going to use our times table. We'll see 6 is too much, so it must be 5. 5 times 24 is 120. We do our subtraction. We're going to get a 15. And now we have to start going into our train of infinite zeros. So we're going to bring down this 0 here. And 150. So it looks like that's going to be 24 times 6, right? So let's write down a 6 here. That's going to be a 144. Subtract that away. We're going to get a 6. We'll bring down another 0. How many times is 24 going to 60? Looks like 2 times. Okay, so 2 times here, that's 48. Let's subtract that. What do we get? 12. Let's bring down one more 0. And oh, look at that. That's going to be exactly 5. So that's going to be 5 here, a 120. We subtract that away. We get a remainder of 0. So we know we're finished. Okay, so 375 divided by 24 is going to be 15.625, terminating. All right, so I just wanted to show you the utility of creating a little multiplication table here for this number. If it's a big number that you're not familiar with, just go ahead and do all the multiplication options here from 1 to 9, because those are all of the possible digits that you'll be filling in over here for the long division. All right, so that was the last fraction that I wanted to convert, but there is one final conceptual question I wanted to pose. And that was why some numbers like 1/2 or 0.5 terminate, but other numbers like 1/3 or 0.3 repeating, they go on forever. Like, is there something special about 1/2 or unique about 1/3 that makes them terminate or not terminate, right? And, the simple answer is when you do the long division of 1 divided by 2, eventually you get a remainder of 0, right? And so then it terminates, and when you do the long division of 1 divided by 3, you never get a remainder of 0, and so it never terminates. That's sort of the simple answer. But really, terminating and these infinitely repeating decimals, I want to say, are kind of an illusion. They're nothing special about 1/2 or 1/3, but rather it's related to how we represent numbers in base 10. If you were to write down, your place value numbers in a different base, then sort of the decimal representation would look different, and maybe it would terminate where it didn't before, or if it terminated before, maybe it's infinite now. So let's look at an example. Let's look at how we count in base 3, okay? Because 1/3 has a 3 here. So I want to talk about base 3. So in base 3, we only have 3 digits available to us. We have the digits 0, 1, 2. And then if you want to write down the number 3, you have to shift up to the next place value and increment it. So this is the number 3. 4, 5, and 6. Okay, so this is how you count from 0 to 6 in base 3. So given this new kind of notation, look at what we're doing. I can write 1/3, but this is written in base 10. If I was to convert this into base 3, it would look like this. So this is in base 3 now, right? Because this 1, 0, that's how we write 3 in base 3. So if I do that, let's do the long division in base 3. I'm doing 1 divided by 3. All right, this is going to go in 0 times. You bring in a 0. And now this is going to go in 1 time. And 1 times 3 is 3. I do my subtraction. I get a remainder of 0. So I'm done. I have now represented 1 divided by 3 in base 3, right? And it terminates. So what I'm saying is, that in base 10, we have a decimal representation of 0.3 repeating. But in base 3, it's going to look like 0.1. it terminates, right? So whether some number, some fraction in decimal form terminates or doesn't, isn't really a special property of that fraction. It's a reflection of how we choose to sort of arbitrarily write things in base 10, right? And that was because our ancestors did math in base 10. But if they had done it in a different base, well, our decimal representations would then be different, right? Okay, hopefully this was a good review of sexy long division and how we can use it to convert fractions into decimals. We looked at terminating decimals and how those result from long division where you eventually get a remainder of 0. And we also looked at infinitely repeating decimals, and those result from a long division where you never get a remainder of 0. And in fact, the remainder eventually starts to repeat itself, and that yields some repeating chunk there. Okay, thanks a lot, and I will see you next time.